In lecture 1, we define pressure. Today we go under the surface. Why does your head feels like it's going to pop at the bottom of the pool? It's all about the weight of liquid column overview. We are driving the most famous formula in hydrostatics, T is equals to rho g h, and finally clearing up the confusion between absolute and gauge pressure. We'll also take our first look at buoyancy, the upward push that makes ships float and rock feel lighter. If you have struggled with these concepts in class, don't worry. We are breaking it down, physics buddy style. Drop your question in the comment as we go and let's dive in.
So let us just quickly revise what we did in the last class and then we'll continue with today's topics. So we discussed what ideal fluid is. We talked about what are the topics we're going to learn here in this particular unit. What are the different topics comes under static fluid and fluid dynamics. We discussed that. Then we talked about few properties, or you can say few phenomena or few things represented by fluid. So one of such things is pressure. We look at different units of pressure again. It is very important because sometimes questions may make it examiner may make question tricky by changing the unit. So that is important. Then we talked about Pascal's law. Before that, we talked about density. Then we talked about specific gravity. We talked about Pascal's law. We looked at the applications of Pascal law and we did some problems. So to start today's session, let's do some problem. Let's do it with a problem. So here we have a question, and question is quite simple. You just have to try to answer what exactly is being asked in the question. So question says that there is an hydraulic press which is used for compressing cotton. Just keep this thing in mind. So area of piston is given. Whatever is given in the question, I'm writing. So area of piston is 0.1 meter square, and the force exerted along the piston rod. So we have given a force which is 200 newtons. Now the question says if the area of larger cylinder is the area of larger cylinder is also given, which is 0.8 meter square. Find the pressure produced in the cylinder and the total crushing force exerted on the bale of cotton. So you have to find out the force which is exerted on the cotton, as well as we
Oh,
have to find out pressure.
okay. So they're asking us to find the force exerted on the cotton.
Yeah.
Okay, find force exerted on the cotton and pressure.
So again, as we're dealing with hydraulic press, so
Okay,
the pressure must
Pascal's
be
principle.
same. Yeah. By using Pascal's principle, we can do that. So
Okay,
first of all, we know that here pressure must be equal on both the ends. So P1 must be equals to P2. This is what we can write. Now pressure is nothing but force upon area. So F1 over A1 must be equals to F2 over A2. From here, you can simply find out F2, which is F1 times A2 over A1. You can simply substitute the values and you can have your answer. That is the force which is exerted on the cotton. Once you find that force, now the question is also to find out pressure. So in order to find out pressure, we can use any of these two pistons. You can
yes,
use
sir.
that. You can use that as well. So pressure is equals to force over area, which is 200 over zero point 0.1, which is 2000 newtons. So this is 2000 newtons per meter square. So this is what the pressure is. Solve this equation and tell me the value of force as well.
Okay. So, so when we had to find pressure, right? That was for to find. Sorry, when we had to find force, that was the force for the second piston, right, sir?
Yeah,
Okay, okay, sir. So now the pressure exerted, wouldn't that also be the same on the cotton?
yeah, pressure is the same,
The force
but
over
we have to find
area, right?
force. Yeah, but we have to find force.
But haven't they already given us the force, sir?
We have to find out force on the larger cylinder. This is the force which is given on
Oh,
the
okay,
smaller
okay. I'll,
piston.
I'll I'll plug it in. So F2, so that's equal to the force of 200 times the area of the second one, which is zero point 0.8, and then we divide that by 0.1. I get 1600 newtons for the second for the larger one.
Yeah, correct. So
1600
here again,
newtons.
we can notice one such thing that we applied force on smaller piston of magnitude 200 newtons only, but on the larger piston, we got almost 8 times. So that is the reason why this hydraulic press or hydraulic machines are also known as force multipliers because they have capability to multiply the force to greater extent. So that
Okay.
is one such use. All right, let's move to the next topic. Now we'll be talking about pressure exerted by liquid column. Then we'll see what are the effect of gravity on fluid pressure and different things. So whatever relations we're going to get here now, these are the most important and useful relations that we're going to use in solving questions. So in order to understand that how much liquid column it can exert pressure, we simply need to assume few things. The first thing we assume here is suppose there is a liquid column and that liquid column is cylindrical in shape. So this
Okay.
suppose this container is completely filled with liquid. As it is completely filled with liquid, so all the water inside must be exerting some pressure on the surface of the container. So this is the bottom, and this bottom is something which is experiencing all the pressure. So the liquid here is capable of exerting pressure on the bottom. So how much pressure is it? That is what we have to find. And that pressure is simply given by force per unit area. So the force which is acting downward is going to be the weight of liquid, and that weight of liquid is calculated using mg. Always keep this in mind. Similarly, base has some area. So we'll assume that the area of base is A. Now, we have to find out pressure. So pressure is nothing but force upon area. And here, the force which this bottom is experiencing is basically the weight of the liquid. So again, you should remember that thing that weight is another kind of force. So here you can write it is weight per unit area. Now, if you remember, what is weight? What we learned about weight? How we are supposed to represent it? By simply writing it mg. So weight is mg per unit area. But again, this is not something we should be using. So in place of mass, now again we have a small relation. As we know that density is nothing but mass over volume. So mass can be written as density times volume. So here we can write density times volume times g over area. Now, if you try to understand what volume is, so here volume can also be written as area into length. So whatever length this liquid column has, let me take it as h. So in place of density, we can write rho. In place of volume, we can write area into height. In place of g, we'll writing g only. So ultimately, we get pressure as rho g h. So this is the pressure exerted by liquid column at the bottom. So this is how you're supposed to find out the relation. Again, it is a very important relation and we'll be using this relation a lot. Is it clear?
Wait, so when you do mg over a, right?
Yeah.
How does that become dvg? Oh, density, right?
Mass.
Density is
Yeah. Yeah.
mass over volume.
Exactly. So mass
Oh,
becomes density times volume and we can write density times V. That is dV.
so dvg over a becomes rho v. Okay.
Yeah. And in place of volume, we can write area into height. So we also know that for writing volume of any specific container, we just need to have area and the height. So height of the liquid column we assumed h and area is A. So A will cancel out each other and the pressure is rho g h. Again, it is a very important and we'll be using it a lot.
Okay.
Now there is a small concept called hydrostatic paradox. Sometimes it is being asked in some questions. Sometimes you just have to analyze and answer few things. So this
So,
might
sorry,
play
sir, The previous formula that you showed me, was that the formula for buoyancy?
No, it is a formula for pressure. For buoyancy,
Pressure.
the formula is V rho G. H is being replaced by volume. So that is a different thing. We'll come to that part as well.
What's rho, sir? Rho?
Rho is density.
Rho is then okay, okay.
We use rho to symbolize density.
Okay, okay. Thank you, sir.
Yeah.
Oh.
So next we have here is hydrostatic paradox. It is a very basic and simple explanation. We don't have to think much. Suppose there are few containers and all the containers has different openings. Like for example, suppose this is the surface on which all the containers have been placed. And we have different containers. One is like that. Another one is like that. And third one is like that. So all the containers are filled with liquid or water. Now what happens here is, irrespective of the mouth of the container, the pressure exerted at the bottom is going to be same for all
Okay,
the
okay.
containers.
Oh, the depth is the same, that's why.
Yeah. So
Oh,
using
okay,
these
okay.
3 points at the bottom, so pressure at all the points must be same irrespective of the shape of the container. This is
Oh,
what
because
hydrostatic
okay.
paradox is. If you want to write the specific statement, you can also do that by using both, although the meaning is same.
Wait, is it, sir, because like if we make a column like with the point, right? Like a column between the points, the number of water molecules directly above would be the same, right?
Yeah, and they will be responsible for exerting pressure at the bottom.
So only the ones directly on top of the point mass.
Yeah, kindly. So let me just give you a small idea about all of these things. So suppose this is a container and this container has different points. I have marked different points on this container. And these points are, suppose this is A, this is B, C, D, E, F, G, H, K. So these are the different points on the container in the container at different heights and different levels as well. The thing is, you just need to verify or mention the pressure relation among these all these you can say points. So A and B are at same depth. C is at different depth. D and E is again at different depth. F is again at different depth. G is again at different depth. Similarly, H and K are at the bottom. So different points are at different depth. So if you try to write the pressure relation among these points, how we can write it? First of all, we simply know that as depth increases, as you can see in this relation, pressure is somewhat which is directly proportional to h, or you can say pressure is something which is directly proportional to depth. So as depth increases, pressure increases. So just think about it and tell me, out of A and H, which point will have more pressure? At which point will experience more pressure?
H, because there's
Yeah,
more water above it.
exactly. So we can simply say that pressure at H point must be equals to pressure at K point because of Pascal's law. Pressure at same depth must be same. This whole thing must be greater than pressure at G point. It must be greater than pressure at F point. It must be greater than pressure at D point, but pressure at D point must be equals to pressure at E point. Again, using Pascal's law. This thing must be greater than pressure at C point, and pressure at C point must be greater than pressure at A point, which is equals to pressure at B point because of same depth. So if you understood this particular part, you'll be able to solve so many questions on your own, only based upon that. So make sure you keep that thing in mind. Is it clear?
Yes, sir.
Now there are two cases. First case is open vessel. Suppose we have a vessel and which is it is open. It is filled with water and we are supposed to write the pressure at the bottom of the vessel. So what do you think? Will the open vessel has any effect on pressure or not?
The open vessel?
Yeah, if the vessel is open, will it
Oh,
have any effect on pressure at point
which point? Point one.
bottom of the vessel? Yeah,
If the vessel is open, like it doesn't have anything that contains it.
yeah, matlab, think about it.
Assuming the depth stays the same, then the pressure should be the same, no?
Yeah, pressure is going to be constant, no doubt about that. But I'm asking you, we have noted that the depth of the container is h. So if you
Yes.
try to find out pressure at point one, it is not only going to be rho g h. It is going to be more than that. Why? Because there is an atmosphere, and that atmosphere will also exert pressure on the top of the vessel. If the vessel is open, and that pressure is known as P naught or atmospheric pressure. So the total pressure at point one must be P naught plus rho gh, where P naught
Oh,
is atmospheric pressure. So that is the effect of open vessel. So that is something you need to keep in mind. Atmospheric vessel, sorry, atmospheric pressure. So this thing will be mentioned in the question that either the container is open or closed. You have to understand and choose the correct option based upon your learning. Similarly, if the vessel is closed, then there is no such thing will be there. So in case of closed vessels, we observe that pressure at point one will be limited to rho gh only, because if vessel is closed, P naught becomes zero. That is what we need to keep in our mind. Clear?
yes, sir.
Let's do a simple small problem. So question says that the density of atmosphere at sea level is given to us. So density of atmosphere is given to us, which is 1.29 kilogram per meter cube. Assume that it doesn't change with altitude, then how high would the atmosphere extend? How high will the atmosphere extends? Given G is 9.81 meter per second square. So how will you think about this problem? Let's try to understand. So suppose this is the ground, and above ground there is an atmosphere. So we assume that the atmosphere above ground must have some height, like there is a proper height up to which the atmosphere exists. After a certain height, there is no atmosphere. We know that, right? So all the air molecules, they will be capable of exerting pressure at the bottom, or you can say at the surface of Earth. And that is something which we are familiar with. So the question is, how high is the atmosphere if the density of atmosphere is 1.29 kilogram per meter cube? So it's quite simple. In order to answer this, we know that pressure at this point is going to be rho g h. because we are finding pressure due to atmosphere. So we don't need to add any P naught here. Rho is going to be 1.29, G is 9.81, and H is something we have to find. Also, we know that the pressure due to atmosphere is nothing but P naught. And I already told you the value of P naught, that is atmospheric pressure. You can also write it as PA. It
10 to
is
the
1,
5.
yeah, 10 to the power 5. So 1.01 over 10 to the power 5 over 1.29 times 9.81 is equals to the height. So this is the height up to which the atmosphere will extend. Solve it and tell me what should be the value.
Okay. So the atmospheric pressure. So how high will the atmosphere? What is the last word, sir? How high will the atmosphere?
Extends.
Oh, okay. So the pressure of the atmosphere is this. Okay. Oh, pressure is equal to force by area, right?
Yeah, but here we will assume that the whole atmosphere acts as a fluid column. So for
Oh,
that, we
okay.
can find out pressure using rho GH,
Rho GH. Okay.
where pressure is atmospheric pressure, which is 1.01 times 10 to the power 5, and rho as well as the value of G is mentioned in the question. So we can easily find out the height, or you can say up to what it is extended, atmosphere extended.
So rho GH. So in this case, would be 1.29
Yeah,
times 9.8, and then that is and then H. We need to solve for H, right?
yeah,
So 2.6 and that is equal to. Oh, so then we can just divide. Okay, so we can divide it by atmospheric pressure, right?
right.
Yeah. Okay. Okay. Yeah. Okay. So rho GH tells you the atmospheric pressure. Oh, so not just tells you the pressure. Okay. I got 7,910.140.
All right, fair enough.
Okay.
And it can also be written as approximately 8 kilometers.
What is the pressure on a swimmer 10 meters below the surface of a lake? Okay. So in this case, the pressure will be rho GH. So 10 times 9.8 times um what is his depth?
10
Or
meters.
the 10 meter? 10 meters. That's very deep. Rho GH. Sorry. What's the what do you call it?
What?
Uh 1 second. The density of water. Oh, 1,000, right? 1,000.
Yeah, you
Oh, I
have to
need to
keep
remember.
that thing in mind because sometimes it is mentioned in the question and sometimes it is not.
Okay, so the pressure on top would be 98,000 pascals.
Pressure on top.
On him, the pressure on him would be 98,000.
But the answer is not correct. Why? Because above lake, suppose this is the surface of lake, this is the swimmer, this is the depth of 10 meters. But above lake, there is atmosphere also. So if there is atmosphere, there is some atmospheric pressure also act on it. So if we are going to find out the
Oh,
pressure,
plus 10 to the 5. Plus 10 to the 5.
yeah,
Okay, that's 198,000.
correct. You can write pascals or either you can write Newton per meter square. So this is the pressure the swimmer will be experiencing at that much depth. So yes, that is important. Is it clear?
Yes, sir.
Let's move ahead. And now let us talk about a very important effect generally object experience underwater. Again, we are still dealing with static fluid. We are not talking about fluid in motion because when fluid starts moving, few other characteristic also appears. So the first thing, buoyancy. What is buoyancy? So you can simply understand this thing as if you place something inside water or something inside liquid. Liquid will try to oppose it. Liquid will try to keep that object above it, or because of some extreme or huge weight, it might be possible that liquid is not able to do that. So if we try to explain buoyancy, we will simply say that it is an upward force acting on a body. It is an upward force acting on a body immersed in a fluid immersed in a fluid is called upthrust. We also call it upthrust because this is the force applied by the liquid on a body in opposite direction of its actual opposite direction of gravity, you can call it. Or we can also call it buoyant force. And this phenomena is known as buoyancy. So it is a very basic thing. We do experience this from our early school days as well. So in order to understand it, it doesn't take much pressure, you can say. So it is an effect. It is the characteristic property of any type of liquid we have around ourselves, and this is what we observe. So based upon buoyancy, there is a famous principle called Archimedes principle. So Archimedes principle actually help us to understand that how much force an object is going to experience due to liquid. So Archimedes principle help us to calculate the force that an object will experience when it is placed inside a liquid. So there is a famous scientist. He was a great Greek scientist, Archimedes, and he gave that principle around 225 BC. So if you just try to understand this thing physically, that how old it is almost 2300 years old principle, like way too old. We cannot even imagine how old it is. Before Christ, it was there. We can assume that how old it is. So according to Archimedes principle, it says, now the statement is important and you need to make note of it. It states that when a body is partially or whole, wholly immersed in a fluid, it experiences an upward thrust it experiences an upward thrust acts equal to it acts through the center of gravity. Center of gravity means the point from where the weight will act of the displaced fluid. Now, if you don't understand this concept well, you won't be able to solve problems. That is the important part. Let me just try to make you understand. what exactly it says. Suppose there are few conditions, there are few cases. We'll be dealing with case one first, and that case is basic one, when object is completely immersed inside liquid. Completely an object immersed in the liquid completely.
Yes.
So you can imagine that there is a liquid column, and in that liquid column there is an object. For the simplicity of calculation, let's take it as a cube. So this cube is inside liquid and it is wholly immersed in, like that. So according to Archimedes principle, whatever upward force liquid is going to exert onto this, whatever upward force liquid is going to exert onto this is called buoyant force. And that buoyant force is equals to weight of liquid displaced. So if the body is completely immersed in the liquid, the weight of liquid displaced will be equals to weight of the body. Make note of this point. If body is completely immersed in liquid, the volume of liquid displaced, and instead of volume I should add rate of liquid displaced. Weight of liquid displaced equals to weight of the body. What does it mean? It simply means like if there is an object and you put that object into the liquid container, so that object is capable of displacing the volume of water as per the volume of its own size. So here FB is equals to weight of liquid displaced, and that weight of liquid displaced is equals to weight of object. So we can simply write weight is equals to mg, but that m should be the mass of liquid displaced. That is the condition. What is m here? M is the mass of liquid displaced. So mass of liquid must be equals to density times volume of liquid. So density of liquid, volume of liquid, and that volume of liquid is equals to volume of object. So this will give us buoyant force as V rho G. Important note point here is density is of liquid, volume is of object. Are you getting it? The density we are going to use is of liquid. The volume we are going to use is of object in case of when object is completely immersed in it.
Wait. So density is the okay density of the liquid, and then so it's so volume will be the volume displaced right by the object.
Yeah, volume displaced by the object. And in that case, the volume displaced is equals to the volume of object itself because object is completely immersed in it. If object is not completely immersed, then in that case, volume of displaced liquid is not equals to volume of complete object.
Okay.
Yeah. Let us do the second case. You'll be able to understand what I'm saying. In second case, we assume object is partially immersed. And in partially, let me take it as half. The object is halfway immersed in liquid and half of the object is floating upward. This will make you understand the complete scenario. So again, same thing you will do. We'll assume a cube and that cube is floating. So what we need to understand here is that when we are going to find out buoyant force is equals to weight of liquid displaced. So how much liquid is displaced by the object this time? That is question. That is the question. So liquid displaced must be equals to half of the volume of the cube. So if I try to write FV here in this case is equals to half of the volume. Again, initially in the first case we have taken the complete volume, but in the second case we're going to take half of the volume. So V rho G by 2. This is what you can write here. Did you got it?
Oh,
Why we took half volume in this case and complete volume in the last case?
yes, sir. Because the other one it displaced all of the volume.
Yeah,
Like the volume displaced was equal to the volume of the object.
yeah. Now just tell me what is this density?
Yes.
This is going to be the density of liquid. Similarly, if you are writing the volume, it is going to be the volume of object. So make sure you keep these points in mind. Clear? Is it clear?
Yes, sir. Yes.
The next thing we have to talk about is law of flotation.
A lot of laws.
Law of flotation. So law of flotation will actually help us to understand that which object is going to sink or which object is going to float. So what does it say? Let us try to understand it. So it simply states that a body will float in a liquid if the weight of the liquid is placed by the immersed part of the body is equals to or greater than the weight of the body. What does it mean? It simply means if the weight of the body is greater than that of buoyant force acting on a body, then body will going to sink. Whereas if the weight of the body and buoyant force acting on a body is same, the body will going to float partially, half immersed in the liquid and half outside the liquid. Whereas if the buoyant force is more than that of the weight of the body, the body will going to float completely. How we can mention this thing? By simply representing this through diagram. So let me just take three diagrams to explain three possible situations.
So I have a question.
Yeah.
Why does buoyancy like go point upwards? Is it like because of some vector thing?
Uh, you should not say this like a vector thing because it is the nature of liquid. It is the nature of fluid. What fluid wants? Fluid wants that the interaction between the water molecules always keeps them together. Like this is a basic property of liquid. Every time, if you just look at liquids, suppose just assume you just spill some water on floor. After some time, you will be able to observe that water will adjust itself in such a way that it will form patches. You won't be able to see a complete film of water lying on the floor. What you will observe? You'll observe that water has accumulated itself in the form of some patches. Some part of the floor will be completely wet as water is accumulated at some points, and some part will be completely dry because water just moved away from there. So what it is, what does it show? It shows the behavior of water molecules, that water or any other type of liquid want to interact with the same type of molecules it has. So water will try to interact with the molecules of its same kind. If some foreign agency or something will come inside it, it will try to repel it. It will try to let it go away from it. That is the reason why water will apply or liquid will apply buoyant force in the opposite direction so that the object can stay away from it. And the force between water and water molecule uh, just try to hold them together so that we won't see water splits. Uh, does it answer your query?
But I thought when you put an object underwater, there's a lot of pressure on it, no?
Yeah, that is also a reason. The pressure is also because water molecules want to push the object away. It just wanted to push it away. The water molecules interact in such a way that they just want to be together, irrespective of what object it is. They just want it to be together. So in this case, if you just observe, I'm taking three cases. In the first case, I assume the object is sink. So if object sink, the reason here is weight must be greater than the buoyant force. In the second case, when object is like that, like it hasn't sink completely, but it is lying about on the surface. And in the third case, water is capable of putting that object away from it, as buoyant force must be greater than the weight. So here, whatever weight which is acting in downward direction, it must be greater than the buoyant force which is acting in upward direction. So in the first figure, weight must be greater than Fv. Now let us try to find out what weight is. So weight is mg, where Fv is v rho g. If I try to write mass of the object, so I can write mass of the object as density of the object times volume of the object. So density of object, I'm writing as rho naught volume into g. This thing must be greater than density of water into volume into g. So if density of object is greater than density of object, sorry, density of object is greater than density of water, object will sink. This is the first case. Similarly, in the second case, we observe weight is equals to Fv. That is, whatever weight is acting downward, it is equally balanced by the buoyant force acting in upward direction. And if you observe such thing, we simply say that density of the object times volume of the object times gravity must be equals to density of water times volume of water times gravity. So density of object must be equals to density of water order to in order to object float, or you can say partially floating. We can say here we'll observe partial floating because it is not something where object is fully immersed, and it is not something where object is fully floating. So it is balanced condition, and that is the condition which is shown by oil droplets. So whenever we look at oil droplets, they always floats on the water. Why? Because of that only. Somewhat the density is almost equal. If the density is completely equal, they will completely immersed into each other. Like if you just try to mix water with water, we won't observe, we won't be able to segregate different type of waters. But if we try to put oil into water, we'll see that oil will float because oil has a little less density. And similarly, if you just try to add salt into water, we'll observe that salt will settle down at the bottom. Why? Because salt has more density than water. So this is the different case that we actually see here. Similarly, in the third case, where weight is obviously less than buoyant force, so in that case, we observe that object will completely float. It won't even get inside. Object won't be able to get inside. So here, weight is less than FV. And the only reason why weight is less than FV because density of object is less than density of water. And this is the phenomena, this is the condition based upon what ships were made initially. Because the density of wood is less than density of water. That is why we are able to use ships made of wood initially. And that is what you must have seen in pirate related movies as well because they use a ship made up of wood only. Because that wood has lesser density in comparison to that of water. That's
Wait,
why
sir,
we made
sir. So if wood was used then instead, then how is metal used now?
relative density by using the concept of relative density. The specific gravity helps us to create a metal, or you can say help us to create an alloy, which is kind of lesser in density in comparison to density of seawater. Because the ships
Oh,
which we uses, they are strictly made to run in seawater, not in lakes. In lakes, we do use ships made of fibers, and that fiber material is again very strong but lesser in density. That is why we are able to use it, and they are able to float. Whereas if you just look at submarines, they are made up of material which is denser than the seawater because it has to stay inside water and has to feel more pressure. So they have to be made of a material which is like more dense in comparison to the liquid, like super dense. It is super dense.
okay, sir.
So there are so many examples here. Again, ship is made up of steel generally, but the interior is made hollow so that it is capable of
Floating.
deal with the force. Yes. It can also displace much more water than its own weight. That is the reason why ship floats and carry a lot of cargo. Similarly, we observe that ice floats on water because of the same reason, because the density of ice is less than that of water. Similarly, if we just look at human body, the human body is slightly denser than the water. That is why if we don't know how to swim, we will sink and we might die. Similarly, a person who can swim in sea water, he or she can swim in river water very easily. So if you wanted to learn swimming, try learning it in sea water. It will make your swimming super easy in river water or
Wait, isn't
in swimming
seawater
pool.
easier, sir? Because the salt makes you more buoyant.
Yeah, salt will give more buoyant force, but it will help you to learn swimming quick earlier.
Oh,
This will help you to obviously easily deal with river water, and there is no such waves or any other rotation of water molecules which it's
yes,
not
sir.
like that sea water has salt, so it will make it easier for us to swim. Sea water has a lot of other things as well. Like there is a continuous waves coming around. There is a vibrational motion of water molecules. The water is kind of having a lot of oxygen inside it as the water is keeps on moving, so it can push you inside very quickly. Whereas river water or swimming pool water doesn't do that those things. So yeah, we have a lot of applications here, and it is very much important to understand that what is the perfect application of this. Let us do some problems and understand how we are able to apply this particular concept in questions. So let me take a very simple question and we'll try to answer what exactly is being asked. So the first question, we have given a body which is having a mass of around 6 kg and is floating. It is floating in a liquid with two by third of its volume inside. So 2 by third of volume is inside. Make note of it. What we have to do is we have to find, first of all, bind force. We have to find bind force acting on the body, and second thing, we also have to find the ratio between the density
Oh, so
of body,
it's like relative density.
yeah, kind of density of body and the density of liquid.
Okay. 1 second. I'll just go to the bathroom very quickly.
All
Yes, sir.
So try this question out. Try to find out the bind force.
Okay. So let's see. A body of mass 6 kilos. So it's P. So FP is equal to PVG, rho VG. So the body of mass 6 kilos is floating in a liquid with 2/3 of its volume inside. 2/3 of its volume. Okay. Find the buoyant force. So if it's floating, then that means the weight is greater than the force of buoyancy, right, sir?
Weight is less than.
If it's floating.
Yeah, if it is floating, means the force acting in the upward direction, that is bind force, is more than the force acting in the downward direction, that is weight.
Oh yes, so the force of buoyancy in this case is more than the weight.
Yeah.
Okay, so FB is greater than weight since it's floating. With 2/3 of its volume inside. So 2/3 of its volume inside means that it's displaced 1/3, right?
Yeah. It displays 2/3.
Oh, displaced 2/3. Okay. So it's 2/3 times 2/3 uh times the density. They didn't give the density, sir. 2/3 G.
When it comes to take density, we have to take density of water because we are finding bind force.
Okay, because they said liquid. I do not know what liquid they were talking about.
If it is not mentioned that what liquid we are dealing with, you can take it as water only. Don't worry about it.
1000, okay, is greater than water. So it's at water 6G. So the G's cancel out. And they're asking find the buoyant force. Oh, the buoyant force is just uh oh, we need to find volume first, right? To find volume. So 2/3 times 1000 times the total times the volume. 2 over
So
3V.
basically 2 by third 3V into V rho G.
No, 2 by third V times 1,000
Yeah. In place of V and rho, we can write 1000. In place of V
divided by
times rho, we
6.
can write, in place of V and rho, we can write mass.
So that would be 6 over 6 times 3 over 2,000. So 6 times 8. So it will be 18 over 2,000. The buoyant force is 0.009 newtons.
No, or 0.009. 40
Wait, wait,
newtons
wait,
it is.
wait. Buoyant force is rho vg, right? So 1,000 times g times 2/3. So the
1000
2/3
times G times 2/3. Again, in place of volume into density, we can write mass because we don't have any dimensions of the object, so we cannot find any value of V. So we cannot substitute V here.
we can solve for it though, right?
How? We cannot find out volume. There is no shape, there is no size given. So finding volume won't be possible.
Okay, so we have to just say 2/3.
Yeah, because the mass is given and also it says that 2/3 of its volume is inside. So whatever it is acting, it must be balanced by this. So
So
buoyant force
two
must be,
thirds g times 1,000. Okay, so it's like proportion. Okay, 2/3 g times 1,000 is what? Let me check. 2/3 times 2 divided by 3 times 1,000 times 9.8. 6,533.333 newtons.
what it is.
I did 2/3 times 1,000 times 9.8.
See, again, when we are finding buoyant force, what is buoyant force exactly?
The
It
upward
is,
like push.
yeah, weight of liquid displaced. Keep this thing in mind, weight of liquid displaced. So how much liquid is being displaced?
Oh, 2/3. Two
Two
thirds times
thirds,
g.
yeah, 2/3 times
Oh.
mg. Whereas what is m? M is the mass of the body. That is buoyant force.
Oh, that's it? Okay, okay.
In place of mass, or this is also V rho g only. 2 by third V rho g. That's it.
We never learned in class that it's the weight of liquid displaced. The teacher made us use the VOG formula.
It's sometimes you'll be able to apply it directly, but in the difficult questions, they will ask you whether you
Or
know the concept or
conceptual.
not. If you don't know the concept, then you won't be able to find out the real actual equation. So that is what it is important.
So it's 6.5
Yeah.
newtons. 6.5. FP is 6.5 newtons. Okay, and then they say find the ratio of density of the body and density of liquid. So that would be the density of the body. Okay, so we can say 6.5 newtons.
Don't have to
Oh.
think much. Just see what is the ratio given of the volume immersed. Whatever volume is inside, that is going to be the ratio of water or the liquid. Whatever volume is
Oh,
outside, that is
PVG
going to be the,
over. Oh yeah, the G's
or
cancel out and the densities cancel out. So the only thing that's left is
yeah,
V over V.
we V will cancel out. The density is something which is left. So we can also write it as V.
Oh, the V's will
You
cancel.
want to,
Yes, yes.
yeah, V rho for body times G must be equals to 2 by third V rho of liquid by G. So G cancel out, V and V will cancel out. Density of body by density of liquid will be 2 by 3. This is what your answer is.
Oh, they already gave us the answer.
Yeah, these kind of questions, they become sometimes tricky if you don't understand what exactly it is. So try to do that question in homework. I'll share the notes in a while and make sure you do this question in homework. And from next class onward, make sure you join on time. Don't
Okay,
be
so
delayed even by 2 3
sorry.
minutes.
Okay, okay. So also one more thing.
Yeah.
They said that it's the liquid with 2/3 of its volume inside. So that means 2/3 of the volume is inside the container. That means isn't 1/3 the displaced volume?
No, no, no. It says that the object is in liquid with 2 by third of its volume inside means,
Oh, 2/3 of the object volume. Okay.
yeah, 2 by 3 is the object's volume inside. So the liquid displaced will be 2 by third. But yeah, again, remember this thing. Sometimes the examiner might use this language that 1 by third of the volume is outside. So they don't mention what is the volume of liquid inside. So
Oh, okay.
what is the volume
Displaces
of that?
2/3.
Yeah, so you
Okay.
just have to figure it out and